Hi, welcome to Teardown Tuesday. I've had this one sitting around for quite some time. This is the Keithley 2400 SMU or SMU source measure unit. And you've seen source measure units on the blog before, so I won't go through all the details. But this is pretty much the industry standard source measure unit, or it was, because it's been superseded by the new whiz-bang fancy touchscreen 2500 model. So anyway, this is still a really great bit of kit if you can pick one up at a reasonable price, but they do hold their value very, very well. And if it's a 0.01% class instrument, 5.5 digits. This particular model, the 2400, there are others in the 2400 series, but this is like the general purpose one, so it goes up to 200 volts output voltage or thereabouts and 1 amp. So it sort of has that general purpose capability. There's other models which have higher current capability, higher voltage, all that sort of jazz. And these things do exactly what their name implies, a source measure unit. They can source both current and voltage, and they can measure current and voltage as well. They're generally used for semiconductor characterization and things like that. So if you want to get the like a modern replacement for a traditional curve tracer, for example, you would have got back in the old days, which can draw your semiconductor characteristic curve of your transistor, your diode junctions, or your, your TVS devices, diodes, whatever it is. These things will pretty much test it. They're designed basically to be automated with PCs and things like that, but they're really precision bits of kit. They really are. So I expect some really nice precision parts in this. I expect it to be very, very well made. It is a very expensive instrument. They sell for many, many thousands of dollars. Like the brand new 2400 one is like, I don't know, $4,000 or something like that. It's got front and rear terminals, GPIB, RS232 interface, none of that new fangled Ethernet rubbish. This model dates back quite some time. Some nice heat sinking on the side, of course, because this is, I think it's 100 watts output capability on it. So yeah, we need some heat sinking on the side. So you know what we say here on the EEVblog, don't turn it on, take it apart. And these are 4-quadrant devices, and I've probably been meaning to do a video on that, and that basically means that it can source and sync current as well, so you can actually so you could use them as a load effectively. So let's try and get this case off here. We probably need some more stuff on the bottom, but I reckon that's going to slide off there. Should slide over the heatsink like that. The warranty void if removed sticker is already broken on this one. I got this at auction quite some time back. I'll link in the auction video down below. I got it with a whole ton of other stuff. So oops, we're coming apart. We're coming apart. Ta-da! Look at this. It's looks very, very nice. Let's come on, you can do it. No? What's going on here? Haha! We're in like Flynn. Check it out. Doesn't that look nice? And surprisingly, I think, quite spread out. The reason I say that is because, look, here's the front panel terminals over here. These will no doubt be low thermal tellurium copper contacts. Same with the ones at the back as well. You know, spared no expense on the terminals, because this thing does have full-scale current range of 1 microamp. So, you know, and 5.5 digits resolution on that. So I think it goes down to, 10 nanoamps or something like that resolution. So it's, so we're talking very low current in here. Not as low currents as the new model, by the way. The 2450 goes an order or two lower than that, I think. But anyway, check this out though. This is the interesting part. We've got our wiring coming over here. We've got some relays down in there, as you can see. We'll take a look at those in a minute. But basically, here is our output terminal, right? And here are our output driver transistors right all the way on the other side here. And I can show you the basic general schematic of this in a minute. But yeah, it's just like, these are our output driver transistors. Looks like down here is our output current shunt by the looks of it, where it's doing some measurement. that's by the looks of things anyway. We've got a main controller over here, which is not the main digital processor, I don't think, because there's a second board right down under this, which has all the digital processing and stuff like that, I believe. But yeah, so that's some sort of maybe, you know, custom ASIC or something like that, some sort of, you know, the high-end converter and DAC, for example. So I just find it interesting that's completely spread out like this. We've got our high voltage driver here driving the transistors. I'll show you that in a minute with the different taps. We've got some isolation slots along here, just some short ones actually cut into there just to differentiate the output driver around here with the rest of it. But yeah, so it somehow has to get from here over to here and vice versa, right across the other side of the board. Interesting. Now, of course, this is a top shelf unit, top specs. You won't find any corners cut in this thing in terms of devices used. So we'll get, you know, analog, top-end analog devices parts, linear tech parts, things like that. So yeah, it's, you know, really precision op amps, and there'll be precision current shunt resistors, precision range set resistors, all that sort of jazz. You know, and the capacitors will be top class, everything else. So that's what you expect from a top shelf Keithley model. And there's the rear panel jacks, and as I said, if they're not low thermal tellurium copper, I'll eat my hat, I think. And we've got that going through a choke here, and they're headed all the way down to a couple of relays down in here. We've got some NECs and a Koto, exactly the same for the front panel terminals here as well. And no surprises for finding a super high quality Koto 8200 series read relay in there. A couple of NEC jobs, they make terrific relays as well, but it looks like that's a probably the high current read relay, so they're using that for the main output switching. USA, USA, USA. Now here's a simplified schematic from the service manual, which I'll link in down below, of the output stage here. So we don't actually have to take off these little sill pads against these transistors to, you know, find out exactly what they are. We've got MOSFETs. Basically, there's going to be 4 MOSFETs in there and 2 power transistors as well. So that's why we've got 2, 4, 6 devices on the upper half and 6 devices on the lower half here. And of course, as I said before, this is a 4-quadrant device, so it's able to source current as well as sink. So we've got our main 225 volt supply rail up here, and then of course it's able to source current out like this. So, but it's also able to sink through these transistors down to negative 225 volts as well. It's supposed to be a negative down there, and you'll notice that these are plus 36 volt, plus and minus 36 volt taps. What are they for? Well, on lower ranges, you don't want to dissipate all the power up here. If you only had your 225 volt rail, if you were down on the lower ranges generating, you know, 10 volts or 5 volts or 1 volts or whatever, you're going to be dissipating a huge amount of power across your power transistor output stage here. So you want to tap in these lower voltages here. So I think they've got a 20 volt range or something like that. So that's what those 2 taps will be there for. We've got ourselves a drive-in amplifier here. Whether or not that's a discrete amplifier, I don't know. You'd have to have a look in there. Could be a transistor amplifier, who knows? But anyway, interesting thing is that they've got a cascode arrangement here. So these 2 transistors, Q516 and Q518 here, are a cascode configuration. You can tell because we've got ourselves basically a common emitter and then a common base joined together configuration, and they do that for the extra output stability, the cascoded transistor arrangement with their sort of, I guess you could call it a hybrid arrangement, because they've got the bipolar transistor and the MOSFET as well. But hey, you can do that, you know, a transistor's a transistor. So that really gains them output stability. The cascade arrangement is really known for its stability. And of course, what you need in this sort of device, really high end, really low noise, really ultra stable, you really need a stable output driver arrangement. And of course, you could go into a ton of detail about exactly how this works until the cows come home, but I'll spare you the details. But yeah, suffice it to say, that pretty much matches the physical arrangement here of the output stage. And you know, as a PCB layout person, when you're actually laying out this product, of course you'd have the designer design this thing. It's usually on a high-end product like this, it's not going to be the same person typically. So yeah, they've designed the output stage, and you go, right, I'm going to do an output stage, and I need to hook it up to a heatsink. It's got to be on the side here, of course. So, and I'm going to physically arrange all of my transistors like that, because that's how it routes out. I don't know whether or not that's positive here and negative here, or vice versa. I'm assuming that the positive is on this side, but hey, you get the gist of it. And here's our high voltage transformer up here, presumably to generate the high voltages required for the 220 plus minus 225 volts. And the capacitors here, we've got a combination of 100 volt Nichicon here. Of course, you get top quality brand caps in this, so they're 100 volt Nichicons for the lower rails. And then we've got I think 400 volts or 350 volt caps up here. These are IC brand Illinois capacitor. They've been acquired by Cornell Dubilier. So, you know, once again, super high quality caps in there. So they're for the higher voltage rails. You notice the big high voltage ceramic ones in there as well. So yes, looks like we've got a couple of those for each rail. So you'd have likely the positive rail, the ground, and then the output, and then the negative rail as well. And there you go. If you've never seen the Illinois capacitor symbol, I see in there. I mean, this is a 13-year-old, a 12-year-old unit. This was manufactured in November 2003. So since then, they've been acquired. But yeah, world-class caps. And there we go, that's likely our buffer driver analog devices AD847. As always, I'll link in datasheets down below. Now, this is an interesting, they've got it in a DIP 8 arrangement, and there's a couple of DIP 8s on this board, and you'll notice that primarily, like, you know, almost all of this is all surface mount construction. But why have they chosen a DIP 8 there? Well, it was the right device for the job. It had the right specs they needed, and it was almost certainly only available in a DIP 8 package, well, at the time anyway. So they used it. They didn't worry about that sort of thing. No compromises. It's the device the designer wanted. So whatever package it came in, that's what they used. And you can see that a few times around here as well. We've got ourselves some AMP 03s, there's a couple of those, and of course you'll get them on the Opto couplers as well. But yeah, there's a couple of amplifiers in there that just buck that SMD trend there. And of course that shows really good design intent, because the designer goes, no, screw you manufacturing, I don't care if that DIP part's going to be a problem for you, that's the part we need. This is a high-end, market-leading precision product. Use that damn part. No substitutes. Thank you very much. And there's quite a few of these spread throughout the board. These are NAIS, top brand of course, solid state photomos relays, AQV214s. So what is this puppy under here? My guess is some sort of custom part, hence, you know, they've got the model on there and they've got some sort of code after that. So I might just lift the skirt on that and have a look. Run at 12 megahertz, whatever it is. Well, that's pretty surprising. In our Tira Max old school EPM 7000 series PLD, not even FPGA. We got a digital beast under there. I expected some sort of analog magic being from Keithley, but no, obviously they're doing that to drive the nearby. Looks like we have a couple of DACs here, so yeah, and maybe something else down here. Anyway, that could be, yeah, just some generic glue logic to drive the various DACs and ADCs required. And yeah, on the upper side of this, we have a couple of serial input DACs. These are analog devices 7849 16-bit multiplying DAC. Not a bad DAC at all. Typical of what you'd find in such a bit of kit. And next to that, we have a couple of precision op amps. The Linear Tech 1112 up here. That's a really nice pico amp input level op amp. The 1097 is a bit more jelly bean, but I don't see a voltage reference next to those offhand, so there's probably going to be one common voltage reference for this whole whole unit, I think, for the various ADCs and DACs, I suspect. And of course, on something like this, high voltage, high current precision unit, you're going to have everything optically isolated, all this entire analog board optically isolated from the digital board down in here. So that's why we've got our opto isolators here. This cable goes down, as I said, the lower digital processing board down there, and the CPLD would handle some of that comms as well between that board, and then just fanning that out to the various ADCs and DACs and everything else. So there's not a huge amount going on in there, but yeah, you've got to have some sort of smarts on the other end of this, because there's too much going on this analog board. So that's just, it takes care of all the housekeeping here. All right, here we go. Let's have a pan around the board with our Teardown microscope, shall we? And we can get reasonably good detail, see all the chips and everything, so everything's hunky-dory. So let's have a look around here, and what I'm specifically looking for is the voltage reference. Now, I found a VREF test point here, but look, it's a linear technology 1097 with linear technology 1007. These are just all op amps. We've got a TI 7705, that's a voltage supervisor, some 74HC logic, a DG for 400 series mux. We've got a max 326. There's nothing special happening here at all. Got some more 74HC discrete stuff all around there. We've got another amp 03 up there measuring across a current shunt, and most likely maybe that's the input there, is it? I don't know, coming from somewhere. I don't think that our precision current shunt resistors are around there. More DG series muxes, they got those everywhere. We've got some precision resistors there. I don't know who they're from offhand, but OP 282s and tons of different types of op amps. Look, AD 797s, 1124s. What have we got? Classic AD 712s there. Just, you know, fairly jelly bean OP 282s, AD 711, which is the single version of the 712 there. Oh goodness, that looks weird on the camera. It looks like there's two holes burned in the chip, but there's not. That's just the shadow coming from the light. You can see it down here as well on the Teardown microscope. So some like LM339s, so a whole bunch of op amps everywhere, a whole bunch of SOT23s everywhere. But these are all op amps, and please scream at me if you can see the voltage reference on here. That puppy looks unusual, but it's an R, so that is a resistor network by the looks of it. So nothing fancy going on there. There's the 16-bit DACs we were talking about before. Mux, we've got some op amps near there. Curiously, we've got a 74F series, fast series TTL. Oh, really old school. So I don't know when this design dates from, but yeah, to put a 74F in there, wow, that's really something. It's got R next to it, so I presume that's another resistor network. More OP177s, 711s, 5534 op amp. Geez, so they're mixing it up. LM311 comparator, and well, I don't know. Scream at me if you can see the voltage reference, because I haven't damn well seen it yet. And there's lots of test points all around, of course, and that VREF has got to be doing something. There's an AD, presumably AD converter test point, but once again, I haven't actually found any analog to digital converters or a reference. Unbelievable. If we go down here to the relays down here, there's nothing much doing down there as well. Anyway, here is our, oops, just hit my microphone. We've got ourselves some Dale precision shunt resistors down in here. They got those in a series parallel combination there. Got some back-to-back diodes happening, and got an opto coupler there, and there's a couple of more of those NAIS MOS relays in there. So this would be our main output current shunt resistor, because it's quite near the output here. It's near all the, there's a output filter inductor, and there's our
It looks like our main output switching relay, the Kodo one. Here's all our wires going off, so presumably that's got to be the main output current sense resistor. So that somehow has to presumably get back into the amp03 over here, because that's our or this one over here, because they're our two closest differential amps for measuring that current shunt. But geez, I mean, I've got some MOSFETs down here, but oh man, where is the voltage reference? I don't know, I must be blind. Looks like we've got ourselves some precision polystyrene caps there. They'd be using those for stability. Got a couple of more precision resistors tucked away down in there by the looks of it. Looks like we've got ourselves a big ass precision resistor, 2 meg up there. So that's doing some high range shunt stuff, presumably. I don't think it's just there for protection, but hey, you know, when it's 2 meg and you use one that size, you know, is it a high voltage one? But there's our output stage for those who wanted to see the output stage. The light isn't the best on this Tegano microscope when you're just using it for, you know, when you're using it for high components. It's only got the one light at an angle. Anyway, I'm still not coming close to an ADC or a voltage reference. Unbelievable. And if you're wondering what that Cal ST5400 is there, that's a high-speed MOS quad FET analog switch array. So yeah, that makes sense. That's all fine and dandy. Now, based on the fact that I can't find a dedicated ADC chip in here, and of course the precision high-end performance of this thing, it's a 5.5 digit converter in the thing, it must be, by deduction, absolutely must be, I have no doubt, implemented in the Altera Max PLD. They're doing a multi-slope conversion in there, similar to other high-end multimeters we've seen before. So, yep, some sort of you know, charge balancing variation of a dual slope converter, or a multi-slope converter. It won't be just a dual slope, sorry. So that is, yep, that's exactly what they must be doing there, but I still don't know where the voltage reference is coming from. I might be able to power it up and measure that perhaps, but I still don't see the voltage reference. But yeah, that's what they're implementing the PLD in there and talking to the ADC over there. So obviously it must do some, there must be some other interfaces coming from the microcontroller to do all the range switching and other miscellaneous housekeeping stuff. But that one, so that could be done somewhere else, but that could actually be dedicated just to the ADC itself. So sorry to all you volt nuts out there. For the life of me, I can't find the actual voltage reference used for the multi-slope converter in here. Could be one of the SOC23 packages, could be a precision buried Zener reference, for example, something like that perhaps. Well, there very well may not even be a specific voltage reference in here. It may be that the rails are, you know, ultra low noise, ultra low drift voltage rails, for example, and everything is referenced from that perhaps, because of course you don't need an absolute reference in there, like an absolute precise value reference like 2.50000 volts. I mean, as long as you've got a power supply that is stable, i.e., you know, however many ppm drift this thing is, or ppm reference, you know, 5 ppm, 10 ppm, or whatever it is, then as long as your power supply doesn't drift, then, well, you can use those as your voltage reference. So maybe that's what's going on here, but I don't know. I'd need the specific schematic to figure that out. And sure enough, it pays to read the service manual. It turns out that the PLD here is the ADC, as I suspected. It's the control element for that. And yes, it is a charge balancing multi-slope converter. That's the only way to get the performance you expect out of an instrument of this class. And no, there are no parts on the bottom of the board. I've had a look in there. Down the bottom here, we've got ourselves the digital control board. It's not worth taking apart to look at. It's just a 68 332 micro controller with driving some GPIB. Nothing fancy whatsoever. Deep down inside there is the power supply. So there's switching power supply down in there. There's a metal shield separating them all. It would be, I think, quite a pain in the ass to take this sucker apart. I'd have to take out all the heat sinked components and lift everything out. No, it's looking really messy. So sorry, I don't think I'm going to go any further with that today. Nothing interesting in a switch-in power supply and just a dumbass micro controller board. All the interesting stuff we want to see is, of course, on the top, which we've taken a look at. And there really is a lot of analog goodness going on in here. It is actually quite complex. If you've got the schematic, yeah, I don't know, you may not be able to make heads or tails of it. It is quite a complex measurement system and range switching. Of course, it goes from anywhere from, 500 volts down to millivolts and 1 amp down to 1 microamp. So it scales, quite a significant range there. And the output drivers, that's an art in itself. All the output stage there, the multi-slope conversion, which Keithley no doubt have a patent on that. Agilent have got their own system, as we saw in the 311 6A multimeter and so forth. And yeah, they all have their particular flavour of implementation, but that is really quite a nice design. It's, impossible to fault that. There's no bodges on it, but it is a very well-proven design over decades, really. So, I mean, this one was manufactured in 2003, but I think it even predates that. I think it came out before that, and it really is quite a nice example, as I've said, of the design-driven aspect to this. It's not driven by anyone else. It's driven by the design side of things, the engineers who actually designed it to meet the really awesome performance specs of this thing. And they said, yeah, we must use that device. We must use that. Available in dip. Doesn't matter. All the different types of op amps and switches on this. It's not like they've gone in there, oh yeah, we'll just use an Oppo 7 for everything, No, they've chosen very specific parts for very specific purposes. On both like the high voltage side of things over here, you're going to use high voltage muxes, the 2 precision current shunt differential amplifiers, and I'm sure if you looked in the type of precision resistors they've used in here, the polystyrene caps, for example, and they've chosen these parts very specifically to get the best performance possible, or the performance that they wanted anyway out of this thing. It's not, absolute world best performance, but yeah, these are a really nice, accurate bit of kit. And I mentioned right back at the start, here's our I/O terminals over here, our wiring to those, and our output stage is right at the back here. How are they getting it across? Well, I think it's differentiated by the cutouts, those little slots in there. There's our high voltage driver over here. Here's our output stage. It comes around. We've got some high voltage muxes over here. We've got the big 2 meg precision resistor over there for high voltage, and that's coming down here. And I think that's coming through this stage, which is where our output current shunt resistor is, and then it's going directly to our switched output terminals there. So I think that's the general flow of things. And here's our block diagram. We've got our voltage DAC and our current DAC over here. These are the 2 DACs that we would have seen over here, no doubt. And then we've got our voltage and current clamping, where that's actually happening in here, I'm not sure. But we've got some error amplification, and then our high voltage output stage, which we're seeing, well, switched high and low voltage output stage. And then we've got our sense resistors that, as I said, I think flows around here. So we've got our current limits, our limiting stuff's probably over here somewhere, and then flows around here to our output sense resistors there, which is down there, and Bob's your uncle. We've got some feedback and stuff like that, all sorts of mucks in, got some overload protection and stuff like that. But that's about all she wrote. It's I'd love to see a more detailed block diagram of that and the schematics. So if anyone does have the schematics for this thing, if it is available online, please leave it in the comments. Yeah, anyway, it is quite a nice design. I hope you enjoyed that look inside a Keithley 2400
source measure unit. Very high-end bit of kit, and if you can pick up one of these, I highly recommend it. There's nothing like having an SMU for doing characterization of basically almost any type of component you can think of. They're absolutely fantastic devices, and yeah, I've done separate videos on that. I'll have to try and link them in if possible. As always, high-res teardown photos of this, mainly just the board really, because I didn't tear down the rest of it. Sorry. But yeah, high-res teardown photos available on EEVblog.com. The link to that is down below somewhere, or up above, depending on where you're reading this. And as always, if you liked it, please give it a big thumbs up. And if you want to discuss it, jump on over to the EEVblog forum. Link is down below as well. Catch you next time.